Sounds good. Yeah, thanks, Will.
Leo from powdr, talking about Autoprecompiles, compiler-based acceleration for zkVMs.
Yeah, thanks, Will, for the intro and for the great work on ETH proofs and this event. zkVM precompiles are fundamental for the performance of zkVMs. However, they are quite difficult to write, read, audit, prove correctness of, and scale. It's not sustainable to handwrite these massively complex circuits every time you want to accelerate a gas program. This is not a, thanks Alex, it's not a sustainable design for zkVMs. So wouldn't it be great if some form of gas acceleration happened automatically? This is already happening. Autoprecompiles are automatically synthesized circuits. This is not some futuristic, out-of-reach research we're speculating on. This is something we have code for that works right now and already improves a few major zkVMs. This is obviously a very deep, complex topic. This is a short talk, so feel free to reach out with questions or find me later if you have deeper technical questions. These circuits, aka precompiles, they are generated from the program's basic blocks using old and new techniques, such as profile gate optimization, hot path analysis, something we call hot witness analysis. We don't really call it that, but for the purpose of this slide, I call this. And we're also working on new/old techniques like branch prediction analysis, these kind of things that has been common in the hardware world and seems to apply quite well to zkVMs as well. After these circuits are generated by a very simple process, they are extremely heavily optimized by lots of optimizers we have in the powdr code base, such as static analysis, compile time constraint solving, low degree polynomial substitution, and lots of other super interesting techniques. As the name suggests, this is of course fully automated. It is ISA agnostic. We currently work mostly on RISC-V, but it is ISA agnostic, and it already has comparable performance to handwritten precompiles, as you're about to see, and the security also scales a lot better than handwritten precompiles. Autoprecompiles are fully integrated into OpenVM, one of the main zkVMs out there, already doing real-time proofs on Ethereum. This is a reference benchmark we run often to test the current state of the powdr autoprecompiles. This benchmark does cat check, or 10,000 iterations of cat check, and we have 3 settings here. The pure software version, which just uses the tiny cat check Rust library, it's just doing cat check in Rust, no precompiles involved, and it takes about 800-something seconds to prove it on a certain CPU. If we use the handwritten precompile that comes with OpenVM, we get a 10x acceleration, which is obviously very, very good. But if we use autoprecompiles, we actually get even more acceleration, 11 times faster than the software version, and so 1.2 times faster than the handwritten precompile, actually. If we use this for Ethereum, we're not necessarily interested in replacing the precompiles that are already there, because they are very performant. So we want to use the current software version plus handwritten precompiles that are already there, proving Ethereum. And this is the proof time for some run. And you can see that as we add new or more autoprecompiles, it gets faster and faster. So currently, with OpenVM plus 100 autoprecompiles, we got 1.37 times faster end-to-end proofs, including recursion. It's important to mention recursion here because in the current way that a lot of zkVMs and provers are written, there is quite a big penalty for having a lot of circuits or a lot of precompiles in the zkVM for a certain guest, because the verifier is linear in the amount of columns. It goes into details, but the more autoprecompiles you have, the more penalty you're paying off in the recursion layer. So it ends up being a lot slower, but we already get this acceleration even including recursion. So as more provers maybe move into multilinear settings, this will get faster and faster. With this, we have integrated the powdr OpenVM on ETH proofs as of last week, which is great to compare to the state-of-the-art zkVMs and be part of this race and test our own optimizations with time. What's also interesting is what's after this. What can we improve on now? So as I mentioned just now, recursion has a pretty big penalty on this, but let's say recursion is solved, not a problem anymore. What can we do? How many autoprecompiles can we use? Well, if we use even more, 500 or 1,000 autoprecompiles, And we consider only what OpenVM calls app proofs. So this is before recursion starts. We actually got almost 2x faster proofs already. So if we can actually do even more, so if we could accelerate all the 13,000 plus RISC-V basic blocks that the Reth client has usually, 80% of the trace cells that are in RISC-V right now would simply vanish. So you can maybe see where I'm going with this. This is some analysis that we do often in our benchmarks, which is what's the effectiveness of an auto-precompile. So each RISC-V basic block becomes an auto-precompile. And not all of them are used because of current restrictions on provers. But we know what the effectiveness of an auto-precompile is, meaning how many fewer trace cells do we use if we use that the prover has to commit to if we use an auto-precompile instead of a RISC-V basic block. So after our new optimizers integration or testing the last 2 weeks, we actually see an almost 7 times average acceleration per basic block in the Reth benchmark. This is also a pretty fun stat. In some basic blocks in the Reth benchmark, we actually see up to 20, 22, 21, 22 times improvements when you take a RISC-V basic block and transform it into a circuit. And interestingly, the EVM interpreter code implementing the opcodes less than and greater than for the EVM are actually among such basic blocks that are accelerated almost 21 times when you make a circuit for it. Of course, a lot of people ask, how are we going to secure all of this? You can't possibly pay enough people to audit and verify this manually. As the whole thing's automatic, we also want to do automatic formal verification. So we have 2 projects going on. One is our own lane 4 rewrite of the optimizer. We want to have fully correct by construction prover, which you can prove in lane 4, and then a verified checker as well that can check when auto-precompiles are generated. We also have a project with the Ethereum Foundation Certora to use SMT-based approaches to prove that every single generated auto-precompile is semantically equivalent to the RISC-V basic block that it came from. This, of course, also propagates to different zkVMs. And SB1 Hypercube has an initial integration with auto-precompiles that already shows almost twice as fast proofs. To finalize, I wanted to note that auto-precompiles are not just a potential replacement for the precompiles we have now in Ethereum. They're also not just a tool to accelerate Ethereum. They can be used for any guest to accelerate any basic block that we're not even aware that they could or should be accelerated. Auto-precompiles are bridging the gap between zkVMs and zk circuits. They are basically removing the zkVM overhead and bringing the performance of zk circuits to zkVMs while keeping the best UX and DevX that we already have from zkVMs. Thank you.
All right. Thanks, Leo. We've got a couple of questions here. I think perhaps you answered the first one. I'll restate it just in case. Can you give a brief overview of how you plan to formally verify your optimization passes? What spec do you compare against?
Yeah, so the most realistic for now, let me go back to this, is so every auto-precompile generated from a RISC-V basic block, from the instructions in that basic block, and the circuits that verify those instructions. So the first idea here is to take the optimized circuit after all the heavy optimizations and prove that the behavior is semantically equivalent to the RISC-V basic block where it came from. So as long as the original zkVM is formally verified, we keep the same level of security with auto-precompiles as well. We don't reduce levels of security of the zkVM itself. The other approach is a more long-term approach, which is we are writing the optimizer in the whole process in lane 4 as well, so that we can have proof of correctness of the whole algorithm, of the whole code base, and not just prove auto-precompiles as they come out. Hope that makes sense.
Great. Last question. How did you go about defining a basic block, or is it dynamic?
A basic block is pretty easy to identify. If you look at RISC-V assembly code, or most assembly code, you'll have branching instructions, jump instructions. A basic block is basically a non-branching sequence of instructions that ends in a branching instruction. So this is pretty identifiable from compiler-generated code.
Awesome. Thanks very much, Leo.
Thank you.